One interesting exercise to explore is what happens to light when it goes through a slab of glass, like a glass pane in a window. Okay, let's look at this. So we have a medium like the air with an index of refraction n1. A light is going to be coming in from that medium with an angle of incidence theta sub 1 relative to the interface of the medium and the glass. The index of refraction of the glass is n2, its thickness is t. Now, because of refraction, light is actually going to bend towards the normal that we have here in dashed line. Instead of moving on a straight line, it's going to bend. Now, it's going to bend towards the normal because we are moving from a low index of refraction to a higher index of refraction. Or in other words, because light is slowing down. Okay, once inside the glass, light is going to move in a straight line, what is shown here. It's going to continue moving on a straight line till it meets the second interface, and that's the interface between glass and the outside. At that second interface, it's going to have a new angle of incidence. This is the angle of incidence it's going to have. It's going to refract again, but this time it's going from a high index of refraction to a low index of refraction, from n2 to n1. So because of that, the emergent beam or the refracted beam is going to bend away from the normal. Here the graph claims that the new angle that the beam is going to have with the normal is going to be the same as the original angle of incidence. Okay? We'll try to explain that in a little bit. So, but the bottom line, the beam, just because of the path it's going to travel in the slab, it's going to actually be displaced. It's going to emerge at a position that's slightly different than the original beam. Now, the direction of the emergent beam, according to what we are saying here, is going to be the same as the direction of the original beam. Okay, let's look at this. First, let's consider what's going to happen at the first interface. At the first interface, what we do have, this is my angle of incidence theta sub 1. This is my angle of refraction, let's call it theta sub 2. Theta sub 1 and theta sub 2 are related by Snell's law. So I have n1 sine of theta 1 is equal to n2 sine theta 2. Now, that's the relationship between them. If we know n1, theta 1, and n2, we can find theta 2. Now, let's look at what's going to happen at the second interface here. For that second interface, this is my angle of incidence. But since this top dashed line here is parallel to this bottom dashed line here, this angle theta 2 is the same as this angle here. So my angle of incidence for the second interface is going to be theta sub 2. And Snell's law for the second interface is going to be written as the index of refraction, which is in this case n2, times sine of the angle of incidence, sine of theta sub 2. And then that should be equal to n1 sine of the new angle of refraction. Let me for a second forget that this is here, and let's call it theta sub 3. Okay, now if you compare both equations, this is the same as this, and this is the same as this. So everything is the same except theta 1 and theta 3. So that tells me that theta 3 is actually equal to theta 1. And that tells us that the emergent beam is going to be the beam here is going to be parallel or in the same direction as the incident beam, this beam. Okay, that's good. Now, what if we would like to know by how much the beam is going to be displaced? If we would like to do that, again, we are going to use a little geometry. Okay, how are we going to use the geometry? Once we use Snell's law, that means we are going to know what theta 2 is. If we know what theta 2 is, and we know t, we can actually find the length of the beam here. Let's call that length L. So what we have, if you look on top here, we have a right angle triangle. So cosine of theta 2 is going to be equal to the adjacent, which is the thickness, over L. So L is the thickness over cosine of theta 2. Okay. Now that I know L, I'm going to look at something different. Because my goal is not to find L, my goal is to find D. D is the displacement here, it's the same here. So let's consider this other triangle. I'm going to do a little erasing. Let's consider this other triangle. The hypotenuse is L again for the triangle, but the opposite side is D. It still has the angle. Okay, actually, let me be careful. Let me erase this. So the question is, what is this angle? We know that the angle from here to here is theta 1, and we know that this angle is theta 2. So that tells us that this angle is theta 1 minus theta 2. And then the sine of that angle is equal to D, what we are looking for, over L. So if I'm trying to find D, so I'm going to continue here. So D is going to be L sine of theta 1 minus theta 2, which is equal, replacing L by its value here, t sine of theta 1 minus theta 2 over cosine of theta 2. So we have it all. Okay, that's a good exercise. Okay, now let's consider something else. What happens to the colors of light? What if we are shining white light here? Is the slab going to disperse the colors? And the answer is no. Why is it no? Because for whatever color light, we are going to have an N1, N2, and another N1. Now, all beams are coming in with the angle theta 1. So it is true that N2 for blue is going to be different than N2 for red, which means that inside the glass, blue is going to bend differently than red. Okay, now the fact that it bends differently than red means that the beam inside is going to travel a different path. However, when the beam reaches this end, we are going to use the same Snell's law. So it's going to reach the end of the slab at a different location. However, it's going to come out with the same angle theta 1, because again, we are going to apply whatever we did here. Instead of just N2, it's going to be N2 blue, and then N2 red. That does not change much to the equation. We are going to again find that theta 1 is equal to theta 3, meaning that the light beam is going to emerge, all the light beams, even though they are slightly displaced, they are going to emerge out with the same angle as the incidence angle. Because they are going to come out at the same angle, we are not going to be able to see them separated. The way they are going to come into our eyes, they are going to come parallel, so they are going to just add up without us noticing any difference. An interesting question is to find how much separation do we have for a particular thickness of the slab. But that might be a good exam question, for example. Now, another interesting thing is more elaborate shapes, like this one here. Now, when we have a situation like this, where we are shining a light beam on the end of a particular shape of translucent material. So how do we figure out what's going to happen to the beam inside? We just repetitively apply Snell's law, the law of reflection, and geometry, and of course, now and then, whenever the beam is going to meet an interface from glass or whatever translucent material it is into a lower index of refraction, like air, then we have to check if the beam is going to refract or not. And that's to check if our angle of incidence is smaller or not than the critical angle. Okay, let's examine this particular situation here. Okay, so in this case, so what do we have? Our beam are coming in. Instead of going straight, since it's moving from an N1 that's small to an N2 that's larger than N1, the beam is going to bend towards the perpendicular. This is our perpendicular. So instead of moving straight, it's going to bend towards the perpendicular, and this is my angle of refraction. And again, we find that using Snell's law. So N1 sine of theta is equal to N2 sine of theta sub 2. And that's the way we find theta sub 2. Now, once we find theta sub 2, we can figure out at what angle is the light beam going to hit this interface. So how do we find it out? So we look beyond what happens here. We kind of look at the big picture. What do we see with the big picture? We see that we actually have a triangle here. Since we are given this angle here, alpha, and knowing theta 2, we should be able to figure out what alpha 2 is. How do we do that? Okay, now that we know theta sub 2, we can figure out this overall angle. This overall angle is 90 degrees plus theta sub 2. So let's call this angle, I don't know, let's call it beta. So beta is going to be equal to 90 degrees plus theta sub 2. And then, reconsidering the triangle, what do we know about the triangles in general? One general property, all angles should add up to 180 degrees. In this case, alpha plus beta plus alpha 2 should be equal 180 degrees. So in this particular case, then we replace beta by 90 plus theta sub 2 and solve for alpha 2. So alpha 2 is equal to 180 minus alpha minus beta, which is minus 90 degrees minus theta 2. So that leaves me with 90 degrees minus alpha minus theta 2. So now we know alpha 2. Once we know alpha 2, we can figure out what theta sub 3 is. Theta sub 3 is 90 degrees minus alpha 2, which is equal to 90 minus that. So that gives me, in this case, the 90s cancel out, and we have alpha plus theta 2. Okay, now we need to check. Are we going to have any light emerging? Theta sub 3 is our angle of incidence here. Okay, to check if any light is emerging, remember Snell's law. N2 sine of theta sub 3 should be equal to N1 sine of, let's call it theta sub, I don't know, let's call it theta sub O, since we are checking it out. Now, to find the critical angle, I'm going to replace theta sub 3 by theta sub c, and that should be equal to N1 sine 90 degrees. So sine of theta sub c is going to be equal to n1 over n2, and theta sub c is just sine minus 1 of n1 over n2. Okay, we find theta sub c and compare theta sub 3 to theta sub c. In this particular example, theta sub 3 is larger than theta sub c, which means we have total internal reflection and no light will come out. However, light is going to be reflected, and we are going to find back the same angle theta sub 3 here and the same angle alpha 2 here. Okay, let's go further. Once we have that, we know that this angle is alpha 2. Okay, using again geometry, we can figure out that this angle is alpha 2 as well. If that angle is alpha 2, that's my angle of incidence for this new interface. The angle of reflection here is going to be again alpha 2. What about the transmission angle? We use Snell's law. N2 sine of alpha 2 should be equal to N1, since we are the outside here, N1 sine of theta sub 4. I drew a larger theta sub 4 because we are going to a higher, to a medium with lower index of refraction. And that's the way we find our theta sub 4. We already know what alpha 2, we know N2 and N1. Problem solved.